we'll carry on our discussion about different diagnostic tests and about the assumptions we made about our regression model. We will talk about autocorrelation and specification errors or model specification. As a quick reminder, these are the topics. The green light, the green text is these are the topics that we covered already, and this is where we are in today, autocorrelation and model specification. Next lecture we'll talk more about how to do empirical research, but also I will add some material about time series regressions. So these are the assumptions we made. Last lecture we talked about multicollinearity, assumption 6, and heteroscedasticity, which is related to assumption 4. So we know how to test for multicollinearity or how to detect for multicollinearity, why multicollinearity arises, why it happens, and then what are the consequences when it happens, and then how to detect, and then how to deal with multicollinearity. We also discussed what heteroscedasticity means. Okay, we as assumption 4 articulate this, we assume that the errors have a constant variance. So that variance doesn't change over time or across units or observations. But what if this is not the case? We say this is usually not the case with cross-section data or econometrics or econometric models that are based on cross-section data. So we don't expect the errors to be homoscedastic, so they are likely to be heteroscedastic. But also we learn how to detect for that, how to deal with that, if that was the case. The lecture recording is up now on Hanomics, my YouTube channel. So if you click on that link, that should take you straight to the lecture video. Okay? And of course, if you have any questions, please come to my office hours or send me an email, or just talk to me. If you meet me by chance, it's fine, I don't mind. As I said, today we'll talk about autocorrelation. So just what do we mean by autocorrelation? So this is the first half of the lecture. I'll be talking about autocorrelation, what it means, why it happens, and what to do or how to test whether your errors are autocorrelated or not, and then what you should do in such case. So as you've seen before, assumption 5, we assume that the covariance between two errors, J and Ui, is 0. So that means the errors are not correlated with itself. That's why it's called autocorrelated. So your errors should not be correlated. Okay? So this is something desirable. This is something that we wish to have, that we have errors that are not autocorrelated, or sometimes you could say serially correlated, so because it's correlated with each other. So we hope that this is the case, but what would that mean for us? So if we talk about time series data, again, we explained that before. Time series data, you have one unit. You collect data for one unit. This unit could be a country, could be an individual, could be a household, could be a firm, whatever this unit is. So you collect data for one unit, but over time. Okay? The cross-section data, there's no time in cross-section data. So it's one point in time. You collect data for a large number of units. Again, your units could be anything. Okay? Panel data, you actually have both dimensions. So you collect data for a large number of units, that's cross-section. Over time, that's time series. So you've got both dimensions in your data, so that's panel data. Okay? So if we have a time series data, so that means, for example, these are just some examples. If we experience a disruption happened because of a labor strike that affected output this quarter. We shouldn't expect, if there is no autocorrelation, we shouldn't expect this will affect output in next quarter if your data is quarterly data. Okay, so if you talk about T and T plus 1, so now and the next period. In cross-section data, if we imagine that the effect of an increase of families' income, how this affects their consumption, this shouldn't have an impact on the consumption of other families. Okay, so if there is no autocorrelation. So this is the ideal case when we don't have autocorrelation. Okay, but the problem happens when we have the errors correlated. Okay, in time series data, the example I gave now, if output was disrupted because of a labor strike in the previous time period, so output from this time period is likely to be affected by that. So there's some sort of correlation happening here. Okay, so in cross-section data, it might be very difficult to imagine, but you can think about kind of peer pressure or peer effect or whatever. So if a family has experienced an increase of its income and that leads to increase their consumption, maybe this will have some impact on the consumption for another family. Okay, but you can imagine what I'm talking about here, the autocorrelation problem. It's more relevant with time series data, when you have data order in time. So it's likely the case when you have high unemployment rate in time t, that the unemployment rate will be high in time t plus 1. Okay? Or if you have, let's say, a recession in time t, maybe this will have some impact on time t plus 1. Okay? So when I talk about t and t plus 1, I just want you to understand that I'm talking about time series data. So t means the current period, t plus 1 means the next time period. Okay? So here t, the frequency of your data will explain this. So if you have quarterly data, so I'm talking about the current quarter, this quarter, and t plus 1 will be the next quarter. If you have annual data, so then I'm talking about this year and the next year. Okay? So anyway, so as I said, autocorrelation is something related or more relevant, is a problem that is more relevant to time series data, because this correlation between the errors, as I said, if you have high unemployment rate, you're likely to have in time t, you're likely to have higher unemployment rate in time t plus 1, or if you have low GDP growth in time t, then maybe time t plus 1 will be also low growth. So why this happen? Why does autocorrelation happen? Okay, there are so many reasons why it happened. You could think of most time series, the examples I give, it's actually because of the business cycle. So you see economic activities going up and down. Okay, so that's something embedded into the nature of or the way the economy functions anyway. Okay, so we do see this all the time. So as I said, if you have time with low growth rate, then next time is likely to be very similar. Okay, so this is kind of because of the features of the business cycle. Or it could be misspecification issue, which is something we will discuss in the next half of the lecture today. But for now, if you omitted, if you drop, for whatever reason, an important variable from your regression, okay, so the effect of that the effect of this variable on your dependent variable is actually captured by what? Are you following? Okay, so when the variables that are not in your model, not one of your x's, the effect of these variables would be captured by their term. Thank you. So that means you're following. Okay, so that's exactly the case. So if you drop a variable that is important, that is relevant, then the effect of this variable is actually captured by your errors. and that causes the errors to be correlated. Okay, so again, this could be another reason, and that because of misspecification or a specification error. Okay, something that we will discuss in more detail in the second part of this lecture. Another reason could be, for example, the supply of agricultural commodities, for example, react to price with lag. So if there is a change in the price this season, then the supply will react to this, or suppliers will consider this change in the next time period. So there's some sort of a lag, and that creates this correlation between the errors. Okay, so there are so many reasons. Data manipulation, if you take averages or smooth your data, if you interpolate your data or extrapolate your data. Okay, so there are so many reasons that why autocorrelation happen. Non-stationarity, this is something we might cover, or not slightly. We'll talk about this very briefly, maybe next time, next lecture. But in general, a stationary series means that its features like variance, mean, and covariance are constant over time. So if not, that means the series is not stationary, and that might cause this sort of autocorrelation again. So the takeaway message from this slide is that there are so many reasons why autocorrelation can happen. Okay, so we know, but the first place you need to understand what autocorrelation is. So autocorrelation means your errors are correlated with each other. Okay, so the idea here. Okay, so what is the problem? Okay, how this is going to affect my estimation if there is autocorrelation. Okay, so your OLS estimators still unbiased and consistent. What do you mean by unbiased estimator? Does anyone remember? What do you mean by an unbiased estimator? Yes? Yes. So the expected value of your estimator beta hat equal the true parameter beta. Okay? So if in the presence of autocorrelation, this continue to be the case, which is great. That's something we want to happen. However, they are not efficient anymore. Okay, so that means my OLS are not blue. You remember best linear unbiased estimator? They are not. That's what we want them to be. Okay, so remember we have all these assumptions, and all these assumptions, if they are true, then OLS is blue. But then now, since we lost this assumption about whether the errors are autocorrelated or not, we don't want them to be autocorrelated for OLS to be blue. But now, in the presence of autocorrelation, then that means OLS are no longer blue. Why? Because they are not the best. We lost the best. What do you mean by the best? Best estimator? Smallest variance. Okay, so the one that has the minimum variance. Okay, so if the errors are autocorrelated, that means they don't have the minimum variance, they're not efficient, they're not the best. So we don't have blue anymore. Okay, and that's a problem. So we lose efficiency. We still have unbiased estimators, but we lose efficiency for that. And that means your standard errors might not be reliable as well. Okay? So anyway, so these are the problems, or what would happen if we have autocorrelation. But how do we know whether we have autocorrelation or not? Okay? So the autocorrelation is related to your errors. Then we need to test those errors, whether they are autocorrelated or not. So one way to do that is just to plot them, plot your errors, and see how do we plot the errors. You don't see the errors, remember? You don't know them, you don't see them, you make an assumption, you just made some assumptions about how they behave. However, when you collect data from a sample, you estimate the model, then you get residuals. So your residuals represent the errors. Okay? So what we actually plot is our residuals. Okay, so that means you have a model, you estimate the model, you obtain the residuals, and then you plot those residuals. So when you plot the residuals, and if you see there's like some sort of systematic pattern in your residuals, that means this is likely because of autocorrelation. Okay? So in this graph, all these top graphs show autocorrelation. Okay? So I plot these residuals against time, and the first one from the left, that shows like some kind of cyclical pattern. So that, again, that could be because of autocorrelation. The second one, there's like positive linear trend. Again, that could be a sign of autocorrelation. The third one from the left, that's negative linear trend. But again, that could be a sign of autocorrelation. The last one, okay, that's kind of a quadratic trend. But again, that's again as a sign of autocorrelation. The bottoms, the last one here from the that doesn't show any really cyclical pattern or linear trend or quadratic trend. That sounds like there's no autocorrelation. Okay, so one way to detect for autocorrelation is actually to plot your residuals, okay, and see if there is any pattern. If there is a certain pattern, that means that could be a sign of autocorrelation. So let's now see an example and see how we can do this. And also we'll see how to formally test for autocorrelation. Because what I showed you now is just a plot. Okay, sometimes it might not be very clear when you look at the plot. It's actually always important to perform a statistical test. We'll cover this also in this part of the lecture. So our example here, we have data, time series data. Remember, what do we mean by time series data? So you have one unit over time. Okay, so that's what we have. So we have data from the US, okay, only one country, over time from 1947 to 2000, and we want to estimate a consumption function. Okay, so we collect data about real consumption expenditure, real disposable personal income, real wealth, real interest rate, etc. So these are time series data. So we estimate the model, log of consumption, and we have, this is our dependent variable, and on the right-hand side we have a number of variables, the disposable income, the wealth, and interest rate, etc. So all these are there. So now we want to know whether these errors are autocorrelated or not. What should we do? What we learned so far is that we need to plot the residuals. Okay, so that's why we estimated the model first, because we want to obtain the residuals. So you get the residuals from this estimation, and in EViews you will also see that object called resid, R-E-S-I-D, and that is always has the residual from the last regression you ran. Okay, so your residuals will automatically be there. Once you do the estimation, you will have this in EViews. So I plot resid, that object that called resid. Maybe not very clear what we have, so that's why rather than plotting this against time, actually I'm going to plot the residual in time t against the residual in time t minus 1. To see, because that is the main idea. If your errors or residuals are correlated, then we should see some pattern. If not, there should be no pattern, you remember? So I actually did this by, that's how to graph. I'm sure you're all familiar with how to plot a graph in EViews. So you go quick, graph, and then just to show you how to do the residuals, t minus 1 against the residual. So you just type resid between bracket minus 1. That means the residual in time t minus 1. Okay, the last period. Against resid, which means the residual in time t. So I'm plotting here residual in time t minus 1 against residual in time t. And then you could just choose scatter and then regression line from the options on the right side. And then here this is what we have. So it seems that sort of positive correlation actually. Okay, so my errors from that estimation, from that model are autocorrelated, and actually it seems like positive correlation. Okay, how this affect my estimation here? Can anyone tell me? How does this affect these estimations? We already said that. These are your OLS estimators, yeah? These are your OLS estimation. These are the estimated coefficient using OLS. So your coefficient, your estimation is still unbiased, okay? But it's not efficient, okay? So it's mainly will affect these standard errors. So anyway, so your estimator or your OLS estimation is not blue anymore. It's not the best. Still unbiased, still linear, but it's not the best. It's not efficient, okay? It doesn't have the minimum variance. So anyway, so we suspect that we have autocorrelation. But as I said, you still need to formally test for autocorrelation using a statistical test. The first test we look at is Durbin-Watson test, okay? But before we run the test, you should understand or should know the assumptions under which this test is performed. So these are the assumptions. So it assumes that regression model includes an intercept term. So you have beta naught in your intercept. Regressors are fixed in repeated samples. Error term normally distributed. Regressors do not include lagged values of the dependent variable. So on the right-hand side, you don't have yt minus 1. That's the lagged values of your dependent variable. So there should be no yt minus 1 on the right-hand side. And in that case, it assumes that your errors has some given structure. And that structure is called autoregressive of first order, or AR1. What does that mean? It means that error in time t depends on error t minus 1. Okay? And that's the equation there. So yt, if this is my errors, equal rho, this is the correlation coefficient, yt minus 1 plus another error. Okay? So these are the assumptions for Durbin-Watson test. So you should know these assumptions before you run the test. Before you perform the test, you should know what assumptions that test make. Okay? So this is very important. So this is the structure of your error. And this row, the coefficient of autocorrelation, takes value from 1 to minus 1. Okay? Of course, as it goes to 1 or minus 1, that means it goes like perfectly correlated, or your errors are perfectly correlated. So how to make a decision? Okay? So you will have a test statistic, which is given by EViews. You will see it now. I'll show it to you in a second. But the critical value takes some structure. It has like two values. You have upper and lower value. And this plot here, or this graph here, show you the decision. Okay? So if your D or your test statistic very close to 0, okay, that means you have positive autocorrelation. If it is very close to 4, that means you have negative autocorrelation. If it is around 2, that means there is no autocorrelation. Okay? And that DL and DU, this is the D lower and D upper. So these are the critical values. Okay? So in our estimation, we have the Durbin-Watson. If you look there, the last one here, this one, this one, it's 1.2. Okay? So now what we want to do, we want to obtain the critical value. We want to know the critical value so we can compare. We want to see where exactly this value lies here. Okay? Which region it is. So is it in this region? Is it positive correlation? It is close to 2, so we can conclude that there is no autocorrelation, or it is close to 4, so we actually conclude that there's negative correlation. And also notice these two areas that actually can make a decision between the D lower and D upper, between 4 minus D upper and 4 minus D lower. So between these areas, if your D statistic fall here, that means you cannot make a decision. So it's inconclusive. So what do we need now? We need to know these DL and D upper. So what we need here is this is the table. So what you need to do, you need to know k. K is the number of regressors. Okay, it's not the number of coefficients, because if you add the number of coefficients, that means you have the constant as well, which is this one. So going back here, so how many regressors here? We have 1, 2, 3. Okay, so if it was the number of parameters, that means that there'll be 4. But in this case, with Durbin-Watson, when we look at the table, we're actually looking at k is the number of regressors. So the number of regressors in this case is, you exclude the intercept, you exclude the constant. So that means we have 3. So what we need to look at here is 3, and the number of observation is 54. So you need these two values. So number of regressors and number of observations. So the number of regressors here, 1, 2, 3. The number of observations here, 54. So when we go there, so we're looking at this, k equal 3, okay, because we know we have 3 regressors. And we go down there, the closest one to this is actually this one, 55. It's 1.45 and 1.68. So do you remember our test statistic? Our D is 1.2. So what is 1.2? It's actually smaller than this. It's before that. So going back to our graph, just to make a decision. So this is the lower, which is 1.4 something. So ours actually falls here, which means you reject your null hypothesis and we have positive autocorrelation. And that confirms what we actually saw here in this graph. In this graph, when I plot the residuals against in time t against the residuals in time t minus 1, and then I plot that regression line, it shows actually there's positive correlation. Okay, and that's exactly the conclusion I made using Durbin-Watson test. So this is not a formal test. This is just a way of visualizing your errors and see whether they are correlated or not. You still need to do the test, but the test actually confirms what we found here. Okay, there's positive autocorrelation, or your errors are positively autocorrelated. Remember, we rejected the null hypothesis. So the null hypothesis, no autocorrelation. So going back here, sorry, going forward to this point, you see, so your null hypothesis, so if you're the D statistic or the test statistic very close to 2, then you cannot reject the null. That means there's no autocorrelation. But in our case, it actually falls in between 0 and DL, D lower, because our D lower is 1.4 and our statistic is 1.2. So it's actually below D lower. So we know it falls in this region where actually we have positive autocorrelation. So our conclusion that in this case, we have positive autocorrelation. Okay? What we're going to do about that, this is what we're going to cover after we cover the next test. So because there is another test we could do as well. Okay, so now we know our errors are positively or autocorrelated, and there's positive autocorrelation between the errors. But there are so many assumptions about Durbin-Watson test, and what if we want to go beyond the first lag? Remember the structure or the error structure that we assumed is AR1. Okay, it's autoregressive of order 1, meaning that your error in time t depends on your error in time t minus 1. That's what we assume. What if I want to go back more lags? Okay, so this is, you can't use then Durbin-Watson test. Okay, so there's another test that you could use here. What if also I want to include yt minus 1 among the regressors? You can't, then Durbin-Watson doesn't assume that. So assume that there's no lag-dependent variable among the regressors. So Breusch-Godfrey LM tests actually allow for that. Okay, so it's less restrictive. So you can actually it relaxes these sort of assumptions which Durbin-Watson test assumes. So in that case, it actually allows to have yt minus 1. So lagged values of the dependent variable among your regressors. It also allows for higher order of autoregressive schemes for your errors. So it doesn't have to be AR1. It doesn't have to be only yt depend on yt minus 1. It could be yt minus 1, yt minus 2. Why does it have to be only one lag? Okay, maybe there is a seasonal effect where actually your lags or your errors are autocorrelated in time t. They are actually autocorrelated with yt minus 4 from last year in the same season. It doesn't have to be yt minus 1. Okay, so this correlation doesn't have to be because of just the right or the previous time period. It could be like 4 periods before. Okay, and that's why this one. Okay, so Durbin-Watson test allows only for that, or assumes that there's only AR1 process for your error term. But with Breusch-Godfrey LM test, it doesn't. It actually allows for more than that. So in that sense, now we can actually have, as you can see now, we have what UT, your error, can follow any order, AR process of any order. So here in this case, it's row 1 UT minus 1, row 2 UT minus 2, up to row P UT minus P, and plus some sort of, again, error. Our null hypothesis is the same, no autocorrelation. So Durbin-Watson, for Durbin-Watson, the null hypothesis is the same, no autocorrelation. Okay? And if you want to write the null hypothesis based on that equation, it means that all these rows equal 0, which means that your error in time t doesn't depend on any of the R, or is not correlated with any of the other errors from previous times. Because if row 1 equals 0, row 2 equals 0, row P equals 0, then your errors are not correlated really. Okay? So this is the null hypothesis for Breusch-Godfrey LM test. In EViews, this is how you do it. Okay? So given that we already have the estimation, so you already estimate the model first. Why do you estimate the model first? Why do you need to estimate the model first before you run the test? Why do you need to estimate the model first? Because you need the residuals. That's what we test. We test the residuals. Okay? If you don't have an estimation, you don't have residuals. Okay? So you need to estimate the model first. Autocorrelation is all about the correlation between the errors. We don't have the errors, we don't see the errors, but we have the residuals. Okay? That are based on the sample. So the errors, this come from your population. Okay? Do we estimate the population, or do you have? No, we don't collect data from the population. We collect actually data from the population. So it's sampled based on the population. And that's why when we estimate the model, we get the residuals. That should be a fair proxy for, or representative of your errors anyway. Okay? So we're actually testing the residuals. Okay? But that should represent your errors. Anyway, so you estimate the model, you go to this view menu, residual diagnostics, and then you'll see there serial correlation LM test. Okay? With Durbin-Watson test, it's given already. So once you estimate the model, you have Durbin-Watson statistic in your regression output, as we saw before. But this one, you need to do it. So when you do that, then it asks you how many lags to include. What are these lags? Does anyone remember? What are these lags about? Yes, but this is the error structure. Remember? Yes. So we said with Durbin-Watson, you assume only you go back only one time period, or one t minus 1. But with this test, with this LM test, you can go back as many periods as you wish, or as you think it's important to go back. Okay? So in this case, I just thought, okay, let's try 2. So 2 means I assume that my error actually is AR2, meaning that UT equal row 1 UT minus 1 plus row 2 UT minus 2 plus some error. Okay? So that's my assumption here when I do this 2. Okay? If you think it's important to go 4 lags, go back 4 lags, because your errors might be correlated with 4 time periods in the past, then you should actually do 4. Okay? So these are the number of lags you include. It asks you how many lags to include. So when I said 2, okay, you will see here, this is the model. So what we have here, we have residual as a dependent variable here. Can you see the cursor? Okay, so when I point to that, okay, it's here, and you have, in your regression, you have residual -1, residual -2. This is residual t -1 and t -2, because I said 2 lags. If I put 3 lags, then you'll have 3. So you have 3 coefficients here. Anyway, so now we want to make a decision based on this. So it's very straightforward. This is the statistic here, up there here, but then you have here the p-value, which you can use to make a decision. Okay? If we have a smaller p-value, so if you're looking at 5% significance level, so a p-value below that, then you reject the null hypothesis, which is the case with us now. Okay? We have a p-value of 0.047. Okay, so still less than 5%, so we reject the null. What is the null hypothesis? Does anyone remember the null hypothesis? Guys in the back, what's the null hypothesis? Yeah, no autocorrelation, thank you. Okay, so the null hypothesis, no autocorrelation, is the same like Durbin-Watson. Durbin-Watson has the same null hypothesis, no autocorrelation. So since now we have a small b value, smaller than 5%, then that means we reject the null hypothesis. The null hypothesis say no autocorrelation. So if I reject that, that means there is autocorrelation. It's the same conclusion we made when we actually plot the residuals. They look really correlated. Okay, so our regression now, the second test confirmed that we do have autocorrelation. Okay, so what is the problem with this estimation? If we have autocorrelation, should we care about that? Why should we bother then if it is not important? Why am I spending like half an hour explaining autocorrelation and how to test for autocorrelation? So what is the problem now? We plot the residuals. They seem to be autocorrelated. We did Durbin-Watson tests, tell us they seem to be correlated. And the LM tests show the same thing. They are actually correlated. Okay? So what's the problem? Exactly, it's more about efficiency, the efficiency of your estimators. Okay, so if your OLS estimator is unbiased, but it's not blue, but it's not the best, it's not efficient anymore. Okay, because it doesn't have the minimum variance in that case. Okay, and that is the main issue here with autocorrelation. So now we know we have autocorrelation. How are we going to deal with this? Okay. There are few different ways you can deal with autocorrelation, one of which you can do the first difference transformation. So if, for example, I believe that the errors are the sort of AR1 process, that means UT depend on or equal rho UT minus 1 plus some error. If I actually take the first difference, that means I get rid of that autocorrelation. Okay, and of course you do that for all variables in your. So let me do that and see how would that affect the estimation. Look at Durbin-Watson statistic. How much it is? Remember, this is the first difference regression. Okay, so I took the first difference of the dependent variable, so that means yt minus 1. The same thing applies to the regressors. And now look at my Durbin-Watson statistic. It become nearly 1.9. Okay, should we go back to the critical value, the Durbin-Watson? So 1.6 is your upper, D upper from there, because K here equals 3. So 1.6 is the DU or D upper. Okay, so it is above this one. So that means it falls in this. It's very close to 2. It's 1.9. It's very close to 2. Okay, that means we fail to reject, so we don't reject the null hypothesis, and the null hypothesis say no autocorrelation, so that means we don't have autocorrelation. Okay, so once we took the first difference, we eliminated, we get rid of the autocorrelation problem. So first difference could be one way to deal with autocorrelation, and that seems to be the case in this example, because once we estimated the model using the first difference, now our Durbin-Watson statistic become very close to 2, which means there's no autocorrelation. Okay, there are other methods. Next time we'll when we talk about time series regression, we will include, or we talk about lags and how to include lags in your model. That could be another way. Or you could follow like some kind of generalized transformation in which you estimate actually a value of your row, because we want to know how much these errors are correlated, are autocorrelated. So if we can estimate that row, then we might be able to take this into consideration, into account. Or we could use the new method or hack, which is actually heteroscedasticity, called heteroscedasticity and autocorrelation consistent standard error. Meaning, because the problem that happened actually with heteroscedasticity and with autocorrelation, it doesn't affect your estimation. It doesn't affect the estimated coefficient. It affects their standard errors. Okay, so if we can somehow correct for that, so we take into consideration that our model has autocorrelation, or our model is, or the errors are heteroscedastic or autocorrelated, then we can correct our standard errors. So if you do that, you would have the same estimated coefficient, but what you would have different is your standard errors. So your standard errors will be corrected, taking into account the fact that your errors are autocorrelated or have heteroscedastic error or non-constant variance. So that's probably everything I want to cover about autocorrelation. Just before I move to the next topic, let me just summarize what I said. So all what I said today, okay, autocorrelation is one of the assumptions. We assume that the errors are not autocorrelated, so they are not correlated. Okay, and this is one of the assumptions we made for OLS to be blue, best linear unbiased estimator. But this is not usually the case with time series. So in time series, usually you have autocorrelated errors. So that means the errors in time t are likely to be correlated with the errors from time t minus 1 or minus p. So it could be of any order. We explain why. So there are many reasons for that. One of which we talked about business cycle or data manipulation or model specification. So there's so many reasons why autocorrelation can happen. Okay, but how to detect for autocorrelation? One way, or usually when you deal with when you do any econometrics, you should plot your data, you should plot your residuals, just to have like some sort of visual inspection of your residuals, how they behave, etc. So one way, so we did the same with heteroscedasticity. We always like look at the residuals, see how they behave. So one way is just the informal way. So it's not a formal statistical test. You just plot your residuals, and if you have any systematic pattern, that means autocorrelation is likely the case. Okay. If there's no systematic pattern, then it might be a sign that you don't have autocorrelation. The formal tests, we covered two tests. The Durbin-Watson test, we said it makes a number of assumptions. Most importantly, this that you should have a constant in your regression. You shouldn't have yt minus 1 or any lagged values of your dependent variables among your regressors. And also you assume that your errors structure is AR1 process, which means that UT depends on UT minus 1 only. So you don't go back further back than this. Okay. So given that, you have two values for the critical value for the test. So D lower and D upper. So if your D statistic below that D lower, that means you have positive autocorrelation. If it is above 4 minus D upper, that means it's negatively correlated. So it's in both cases that actually there's autocorrelation. There's an area around 2. So if your test statistic very close to 2, then there's no autocorrelation. And there are two regions where you cannot actually make a decision, which is between D lower and D upper. Okay, how to get the D lower and D upper, the critical values? You need K. K in this case is your number of regressors. So you exclude the constant. Okay, so you don't count the constant. And in our case, we had 3 regressors and the number of observations. So you need K and the number of observations. You go to the table, you find D lower and D upper. Based on our example, we actually found that we conclude that our regression or our errors are actually positively autocorrelated, which we found when we plot the graph anyway. So when we plot the residuals, they look correlated, and they look actually positively correlated as well. The other test which relax some of these assumptions, okay, the Godfrey LM test, the Breusch-Godfrey LM test, that test relaxes the assumption about the lagged value of your dependent variable. So that means you could have yt minus 1, yt minus 2 among your regressors. So that should be fine. And you could also have more than AR1. So you can have an error that is actually that follow a higher order, autoregressive order than 1. So it's not AR1, it could be ARP, it could be anything. It could be AR2, AR3, etc. So we saw how to do that in EViews, and to make a decision, just very simply, you first, EViews already ask you about how many lags to include, and we should understand what lags we're including here. So we include the lags or the structure of your errors. Okay, so you want to test whether your errors in our example depend on error in time t, depends on error time t minus 1 and time t minus 2. So that's why we include 2 lags. But you could go further back than that. Okay, so to make a decision, then you go to the p-value. Very straightforward. If your p-value, knowing that your null hypothesis is no autocorrelation, so if you reject, that means there is autocorrelation. So you reject when your p-value is small, smaller than 5%, for example. If it is large p-value, then you cannot reject. That means there's no autocorrelation. Okay? How to correct for that? One way we looked at is you could have first difference. When we did the first difference, our Durbin-Watson statistic became 1.9 nearly, so very close to 2, so that means there is no autocorrelation. Okay? Or you can apply these hack or heteroscedasticity and autocorrelation consistent standard errors. And as I said, for this method, I didn't explain how it does it, but in general, that's the main idea. If the autocorrelation or the presence of autocorrelation and the presence of heteroscedasticity affect mainly the standard errors, so if we can take that into consideration, we could actually estimate the standard errors correctly, and that will make our estimation blue again. Okay, because the main problem is with the autocorrelation that our estimation is not the best, our estimation is not blue. Okay, so we can make it blue by correcting the standard errors. Okay, and in that case, then you have the same coefficient, but then you have different standard errors which are corrected to take into account the presence of autocorrelation. Okay, any questions? Okay, so let's have a break then. Before we move to the next point, let's have 8 minutes break, please. Okay, I'll see you in 8 minutes. Thank you. Okay, so in this part of the lecture, one of the assumptions we made is no specification errors. That's assumption number 7. Okay. What do we mean by that? No specification errors. In a regression model, you have a variable, dependent variable, that you want to explain its behavior, and you say, well, there's one variable, dependent variable, depend on another a number of variables. These are your regressors or your x's, and you're hoping to include the most important variables. Okay, why? We can't really include all variables. Okay, for many reasons. So mainly we want to include the most important variables. Okay, so but before we talk about the model specification, you should know that there's no such thing like a perfect model. So you should always compare between different models, okay, to decide which one perform better than the others. But in general, what we mean by a correctly specified model, we mean really a very long list of things. Okay, so first, there's no variables that are important and you didn't include. So if you include, if you exclude an important variable, then this is called omitted variable bias. So your estimation will be biased. Okay, so that's like a serious threat to your OLS estimation if you drop an important variable. Why? Because the effect of that variable is absorbed by your errors. Okay? And that causes your estimation to be biased. So that's one thing. So that's the first thing. The second point, again, what we mean by correctly specified model, then you don't include variables that are not relevant, that are not important. Okay? So that's the second point. You see, so we mean so many things by correctly specified model. So one, you don't drop or you don't omit important variables. Two, you don't include variables that are not relevant, that are not important. Three, you actually have suitable functional form. We already discussed that when you talk about log, lin, log, quadratic function, etc. So you should include the suitable functional form. You don't have measurement errors, especially in your regressors, in your x's, okay, and etc. So you don't you need to take into account any outliers in your data, so any extreme values. You need to correctly specify the probability distribution of your errors. You need to have no simultaneous bias, meaning, especially in one equation model where we have y depend on x's, then you assume that x's, the causality goes from x to y. It shouldn't go from the other way. It shouldn't go from y to x. If that's the case, then your estimation is biased again. So we'll cover a few of these points, not everything, but let's start and see how much we can cover. So first example with omitted variable bias. So now let me assume that we have a model, or we want to estimate a model for wage, hourly wage, and I'm going to include some variables, and I will assume that these are not everything, so there are other variables that should be included too. Okay, so we'll start with this model where we have this data on 1,289 workers on 1995. So this is cross-section data. Okay, so in one point in time, you have a large number of units, 1,289. So these are my units, workers, in one point in time. So there's no time really variation. So that means in one point in time, this is cross-section data. So what we have here, we estimated this model. So let's assume that this is the model that is not complete or is not correctly specified because we should have other variables. So maybe we could or we should include experience squared. Maybe we should include experience times female. Okay, maybe other variables are important too. So in this case, this one is called underfitted model because there are other variables that are important that you didn't include in that model. So now we want to know how can we find out. So just before I carry on, before I explain how you can test for that. So first of all, if you drop an important variable, this case is called omitted variable bias because your estimation is biased. So it's not efficient, it's actually biased, okay? So remember when we always talk about the diagnostic test, we always mention that how this will affect our OLS estimation. With heteroscedasticity, with autocorrelation, our estimation is still unbiased, which is great, but not efficient. So we actually suffer from the efficiency, or we lose the efficiency, okay? But with omitted variable bias, it is a very serious threat to your estimation because actually it makes your estimated coefficient biased. Okay, so again, biasness here or unbiased means what we want is unbiased estimator. So unbiased means the expected value of your estimator, which is beta hat, equal the true parameter beta. Okay, in such case, if you have omitted variable bias, that means it's not going to be the case. So it doesn't equal beta; it will be beta plus something. Okay, so because there's the variable that you omitted, its impact actually is absorbed by your errors, and that caused the bias in your estimation. Anyway, so in this case, let's assume now we want to compare between these models or these specifications. So the first specification, which let's call this the restricted specification, where we omitted some variables. Okay, and now we wish to see if what would happen if we include the other variables, or whether we should include the other variables or not. So one test you could use, which is the Ramsey's reset test. So basically, you first need to obtain the residuals from the incorrectly specified model. So the one that doesn't have all the variables, the one that has some variables omitted from it. And then you obtain the fitted values, which is your y hat. Okay? And you plug this y hat in your right-hand side. Okay? And you put the residual, you include this in your model, and then you actually, so this is, the first one is the restricted. The second one, in which you include your fitted values as an additional regressor, this will be the unrestricted. Why unrestricted? Because we include more variables. So the first one that doesn't include everything, that is the restricted model, okay, which in this case, our first one here, this one, okay? So we'll call this the restricted one because it doesn't have all variables. And the one that in which we added the fitted values y hat, so you can add y hat squared, y hat raised to the third power, etc. So we'll come to this point. But at the end, we just include that on the right-hand side. And then we estimate the model. So in that case, our null hypothesis is that your restricted, or the original one, the one we started with, is correctly specified. Okay? So if you reject that, that means it is not. Okay? You have omitted variable bias. If you cannot reject that, then that means the original model is fine, or the restricted model is fine. So use if test, okay, which is you're familiar with. So and if you reject the null, that means your restricted model isn't correctly specified. So in our case here, let's do this. So let's assume that this is our restricted model. We have these variables that we think explain wage, female, non-white, union, education, experience, and then we will obtain the residual, we obtain the fitted values from this, and then we do the Ramsey test. But in EViews, you can do it by going to View, Stability Diagnostics, Ramsey test, and then it asks you about how many terms of the fitted values to include. So I just put 2. And this is the result of the test. So what we can do here, we can actually look at, the p-value. Just want to show you the terms. Okay, so first of all, just before I go to the conclusion, let's see this. So what we have here, these are the 2 terms I added. So you have fitted squared and fitted to raised to the third power. So you have these, because I put 2. If you put 3, then you'll have more. But now this just explained to you what we mean by this step here, number of fitted terms to include, okay? And a good question would be how many we should include. Well, the test doesn't tell us, and this is one of the drawbacks of the test. So we're not really sure about how many we should include. So, for example, I just put here 2. I mean, you can try others, but in this case, when you look at the if statistic here, and this is your probability value, then it's very small, it's 0. So that means you reject the null hypothesis. What does that mean when you reject the null hypothesis? Remember, the null hypothesis is that your model, or the restricted model, is correctly specified. Okay, so you rejected that, so that means your model is not. Okay, so the first model we estimated is not correctly specified. It has some variables that are omitted, or important variables that are omitted from that. So, and that's like it. But as I said, the drawbacks of this test is that how many terms to include, the number of power terms to include. So should we put 2, should we put 3, should we put 4? We don't know. And also, now we concluded that our original model, or our restricted model, is not correctly specified. Then what should we do? The test doesn't tell us. Okay? So these are kind of shortcomings or drawbacks of this test. Okay? It's not really clear. Okay? But in any situation, and in this situation, you probably can try to another model, and then you do the test again and see if you reject, or you fail to reject the null hypothesis. So your null hypothesis is that the model is correctly specified, and if you fail to reject that, then perfect, that's great, this is something we're happy with, that's what we want. There's another way you could do, which is very similar, which is called the Lagrange multiplier, or LM test. The idea here is very simple. If your model is correct, then your errors or your residuals shouldn't be related to any omitted regressors. Okay, so if we omitted some, if we suspect that there are some regressors that are important and we should include, but if it turns out that these are not important anyway and we shouldn't include, that means your residuals should not be correlated with these omitted variables. So what to do then? Then you estimate your model, you obtain residuals, and then what you need to do, then you regress these residuals on your regressors in the original model, plus the omitted variables, the variables that you weren't sure about. Okay? And this is called auxiliary regression, so this is like an additional regression to find out. And what you need to do here is to get the test statistic. In that case, it's n times r square. N is the number of observation, r square, you know what r square is, okay? So the coefficient of determination from the auxiliary regression, okay? The regression in which you run a regression of the residuals from the original model on regressors plus any omitted variables you suspect or you think that they might be it might be important to include them. The test follow the chi-square distribution, and the degrees of freedom is the number of omitted regressors. So if I added 2 regressors, that means these are my degrees of freedom. If I added 3 regressors, that means, so these are the omitted regressors, so omitted variables. So the number of omitted regressors is your degrees of freedom. So if you reject, so meaning if your computed value or the test statistic, which is again it's n times r squared, exceed the critical value from chi-square distribution, which you will see in a second, the t-table for that, then that means your original model is misspecified. Okay, so let's see how we can do this. So this is our original model. So this is the restricted model. Again, I estimated this model. It's the same model. It's the same slide that I showed you before. Wage, again, is female, non-white, union, education, and experience. And we suspect that experience squared, for example, is an important variable that we should include, and also experience times female. So we have 2 variables that we're not sure about. We think this might be important to include, and we want to do this LM test for. So what we need from here, we need the number of observation. So the number of observation here is 1,289, and we need also r squared, which is 0.25 here. So the test statistic is n minus is n times r squared. So that's what we have here. So we have n times r squared. So this is the number of observation. This is r squared, and then this is the test statistic. Okay, and as we said, this follows chi-square distribution, and with 2 degrees of freedom, because we have here added 2 terms here. So we had these, or 2 variables here. Okay, experience square and experience times female. So these are our degrees of freedom. So if you go in the table, okay, so you basically, if you want to look at 5% level, so this is chi-square at 5%, and our degrees of freedom is 2, so basically it's 5.99. So going back here, so we compare this test statistic here with 5.99, and obviously this one is greater than this one, so that means you reject the null hypothesis, which means your actually model is misspecified. So the original model is misspecified. Okay, so just, again, it's another way to find out whether your model is misspecified. But again, there's no suggestion what to do. But since that you suspect there are variables that are important or might be important, then you try again to include one of these variables and try to do the test again and see whether if you fail to reject, that means that great, you're now this is the correctly specified model. If you reject, that means you need to try another specification. Okay, so this is the first problem, as I said. So we can have if we have underfitted model, meaning that you have omitted some important variables, and that is very serious for your estimation because it causes your estimation to be biased. Okay, so your OLS estimator will be biased because of your omitted variable. So omitted variable here meaning it's an important variable that affects Y, that affects your dependent variable, but you did it for whatever reason. So for one reason or another, you just drop that variable from your regression, and the effect of that variable obviously will be captured by your errors. Okay, that your estimators now are biased because of the omitted variable, and it's a very popular case. It's called omitted variable bias. So we saw how to test or how to do some tests to see whether our model is correctly specified or not. On the other side, so these are the underfitted models, meaning that you drop some important variables. On the other side, there's overfitted models in which you actually include variables that are not relevant to your dependent variable. So that shouldn't be there. Okay? So basically, we decide on the variables that we include on the right-hand side based on theory, based on empirical work, based on intuition. But sometimes people think, okay, the more variables I add on the right-hand side, the higher R squared, so that means my model is better. Well, this is not correct. Okay, so this is not necessarily true. So people might just include variables because they see, oh, it sounds like a better or a higher R square, so great, we have a better, but this is not true. So this is the problem of overfitted models, where you actually include variables that sometimes are not very relevant, are not economically meaningful, so actually you shouldn't include them. So in our model here, I think again, I'm following the same example. I'm trying to add. So I have a model where we have female, non-white, union, education, experience. These variables should explain wage or hourly wage, and for whatever reason, I thought I'm going to include age. Okay. Well, that's what we have. I'll show you. Remember when I talked about multicollinearity last time, and I said I'm not very worried about perfect multicollinearity because you will be warned about it by the software you're using. But the problem is with imperfect multicollinearity, because the software will give you results, is not going to warn you about anything. This is a typical case of perfect multicollinearity where you have no actual estimation. So EViews give me an error message. And it's very clear, say, well, your regressors may be perfectly collinear. Why? Because I added age. Which variables in this estimation is likely to be perfectly correlated with age? No, experience. Okay? So there might be some correlation, yes, but it's not going to be perfectly correlated. Okay? So the one that you can try, I mean, you have the data, you can try with education, see if it's perfectly correlated or not. It might be perfectly correlated in this data, but generally, I would imagine that people who are more experienced, they are older, so there's some sort of perfect multicollinearity here, or so they actually, I didn't have, so this was just an attempt to add a random variable or a variable that I thought it might be important, and I added there, and actually the program didn't give me any result. So I run a regression of experience on education, and you see the R square is 0.9. It's very highly correlated, these two variables. Okay, so this was just again another like I mean, you could add some. I could create like some like random variable or variable that is not related to wage at all, and I actually did that in one of the other lectures with the master's program, and I actually create two variables that are not related in any way, so they're not actually part of the data set. I just created them by myself, and then you might have some estimation, but again, you actually overfitting your model because you're including variables that are not important. But as you can imagine, these are not as serious as omitted variable bias, because your omitted variable bias, it affects the OLS estimation. It become biased because of that. But when you add variables that are not relevant, And they should typically, you should find them statistically insignificant, so they're not related to your x anyway. Your y anyway. But in our case here, I just had like an extreme example when I wanted to add age, and it turned out to be perfectly linear with experience. So these are two cases of specification errors: underfitted models and overfitted models. So underfitted models when you omit important variables, overfitted models when you actually include variables that are not relevant. Okay? So another case of specification error is related to the functional form. Remember, when we discuss this in one of the lectures, we said, well, we could have log-lin model or lin-lin model or log-lin model, or maybe lin-log or log-log. So there are different ways that actually can estimate a model in terms of the functional form. But in all cases, we make this distinction. We said what we care about here with OLS, what concerns us is the parameters. As long as your model is linear in parameters, then you can use OLS, so that shouldn't be a problem. What we're talking about here is variables. Okay, so the log is attached to the variable, not to the parameter. So log, or when I say log-lin, I'm actually talking about the parameters. Sorry, I'm talking about the variables, not the parameters. Okay, so the parameters are linear, and that's why we use OLS. So in this case here, I'm just comparing between linear and log-linear models. So in this slide, you will see wage against the other variables. This is a linear, so a lin-lin or linear model. Against this one is log-linear, so wage here, the dependent variable, is in the log form. And what you could do, you could actually try to estimate this or try to run some kind of a test to see which one is preferred, which functional form is preferred. Is it the linear model or is it the log-lin model? So in this case, what I did here, I just generated. This is a new variable, which actually is just the wage average. So this is how you create it in EViews. So you can, to create this variable, you can. I don't know how to. Yeah. Sorry. Oh, yeah. So, and to create like a new variable, so you generate wage new, and this is wage based or wage divided by wage average. And wage average, how to create it is actually, you can say equal, generate wage average equal at mean wage, so that will actually average the wage. So, and then we'll run both regressions, okay? The linear and the log linear using the new variable. And we obtain the residual sum of squares from both models. Just remember, these are our models. So this is one. So here I'm having wage new, so that means it's the linear one. And here the log of wage new, so this is the new variable which I created using the log form. So now all what I need to do is to obtain the RSS, or the residual sum of squares from these both regression, and then we can do this, compute this statistic. So this statistic, this lambda here is n over 2. This is the log of the RSS1. One RSS1 here, this is your larger RSS. So you have the large value here from the regression, whichever regression, and then the smaller one here. And then once you get this one, the test statistic, all what you need to do now you have the computed value, which is very, very high. 365 is very large. So that means it is significant, which means the one with lower RSS is the better, and in that case is the log-lin. So that means the model with linear specification is actually misspecified. So in that case, I should actually use the log-lin. So this was, again, just another way or another type of specification error, which is the functional form. Okay, so just go back to this. So all what I did here, we'll talk about this. Yeah. So now I have to, I'm trying to compare between two functional forms. Should I use, I have a wage equation, a number of regressors on the right-hand side, and I'm not sure now, should I use wage in linear form, or should I use log wage and the other side in the linear form, which is the log lin form. So what we did here, we created a new variable, which is the wage divided by wage average, or the mean value of wage, and this is how you can create it in EViews. And then we run the regression once with the linear form and the other time with the log lin, so the one that the functional form that we're comparing with, and we obtain the residual sum of square. So you divide these two from both regression, you divide these two, and the larger will be in the numerator, and then you get the test statistic. So your test statistic in this case was very large. That means we reject the null hypothesis, which means that the one that with the lower RSS, or residual sum of squares, is the better, and in that case is actually our model with the log lin. So in that case, the linear model is misspecified, and the log lin is actually more preferred to that one. So again, this is another example of a specification bias. So before I just carry on, I will finish with this one. So this is the last case I will cover, so I'm not going to cover the rest. But as I said, when we talk about a model that is correctly specified, you should know that there's no such a perfect model. So you always should compare between different specifications, okay? Just to find out which one perform better. So the examples that we cover today related to a model specification is, first one, the omitted variable bias. We explained that when there is an important variable that you omit, the effect of this variable is captured by the errors, and that makes your OLS estimation bias. Okay? We saw tests, two tests how to do that, the LM test, the type test, the Lagrange multiplier, and the LM test, and the Ramsey test. Okay? We saw how to do that. So this is one. The overfitted model, when you, so the first type of misspecification is the underfitted model, when you omit some variables that are important. The other side, or the other case, is when you have overfitted model in which you add more variables that are not relevant, or you add variables that are not relevant. The third case, when we talk about the functional form, then you can actually compare based on some, again, some tests like this. The last one, which is the specification or the measurement errors. And the measurement errors can happen with your dependent variable or with one of your regressors, one of your x's. It is less serious when it happens with your dependent variable. It's more serious when it happens with your independent variables. Okay, so it's still a problem. I'm not saying it's something that you should ignore. I'm just saying when it happens with one of your regressors or one of your x's, it becomes more serious. Okay, so when it happens with your y, with your regressand or with your dependent variable, that means your OLS estimation is still unbiased. Good news, okay, for us. So, and your variance and standard errors, fine, but the problem is, or the main issue here is that they will be will be larger than the case where your dependent variable is measured correctly. Okay, so in that case, it's not very serious, but it's still a problem. But it's more serious when you have your regressor or the measurement errors happen to your regressors or happen with one of your x's. Okay, so in that case, your OLS estimation is biased. That's not good news. Okay, we don't want our OLS estimator to be biased. Okay, it will be actually biased, and that is the main issue. Okay, so and also if you have an error with a single regressor, so with one of your x's, so I don't mean here with all your x's, only one of your x's, it will be actually lead to bias estimation to the other coefficients as well. So it will affect your estimation for other coefficients or for other regressors. Okay, so even if it happened with one, so that it's more serious problem. So it's very serious problem because again it will cause your estimation to be biased. So in that case, then what is very easy is very difficult to establish the size and the direction of the bias, because if it was possible to know how much the bias is, then you can take into consideration the size of the bias and the direction of the bias. So if your expected or if your expected beta hat equal beta plus something, then you can just take that away, so you know exactly how much the bias is and the direction of that bias. But it's not difficult. It's not easy, to do that. It's very difficult to establish this sort of the direction and the size of your bias. So you could, if there's no way to obtain to measure your x's correctly, then you could use an instrumental variable or a proxy variable for those variables that you think they suffer from measurement errors. Okay, so and that's what I want to cover for this point. So as I said, so what we cover so far in the model specification, omitted variable bias. Let me just go back and just tell you what I didn't cover. So let's go back to these. Yeah. So when we talk about a model that is correctly specified, then we mean that you don't have any, or you didn't exclude any variables that are important. Okay, so we cover this point, and we know that if you drop an important variable, your estimator is biased. So your OLS estimation is biased. And we saw how we can use Ramsey's test or other tests for that. And also we looked at the case where you can, when you include irrelevant variables, okay, it's not as serious as the case when you omit variables, because it makes your, when you omit important variables, it makes your estimation biased. And also when we talked about the functional form, we didn't talk about this in much detail because we actually covered this before. We know about the differences, how to interpret the coefficient, etc. But in this lecture, we just wanted to see an example of how we may compare between different functional forms. And also we talked about the measurement errors. Okay, so when we talk about measurement errors, this can happen with your y or with one of your x's. If it happened with your y, okay, it is an issue, but at least your estimation is still unbiased. Okay, but when it happened with your x's, that is more serious because your estimation tends to be biased. Okay, we don't want that. Okay, so and in that case, then you may use like a proxy or another variable, an instrumental variable that actually represent. So it enters your model to represent that x that you cannot measure without any measurement errors. So we didn't talk about outliers. We didn't talk about the distribution of the error term. We didn't talk about simultaneity bias. So that what we mean by that, we mean that in your model, when you have an equation, so your causality should run from x to y, not the other way around. So when you have a model, we assume that x determine y. So the causality run from x to y. And we said before, causality is established based on theory, not from your regression, because EViews will not warn you. So if you put it the other way around, EViews will give you estimation. So you will give you results, okay? And you might interpret those results, but they're not correct, okay? So when we talk about causality in that sense, just remember causality is established by theory, based on theory or intuition, not based on regression. Regression does not establish causality. So in that sense, we assume now, since you have a model that you have y depending on x, so basically x causes y, not the other way around. And if it happened that it happened in both, so that is again another bias we didn't talk about. But you should know, you should at least understand the idea that there's your estimation will be biased. And again, it's a problem we don't want to we don't want to see. So that's that's everything we covered in this section. And of course, in the first section of the lecture, we talked about what did we say? Autocorrelation. Sorry. So we talked about autocorrelation in the first part of the lecture. Next lecture, as I said before, I might talk about time regression, time series regression, and also we'll talk about doing empirical research. Do you have any questions? Any questions? Okay. Thank you so much. I'll see you next week. Thank you.